DeepMind. This is a joint work with Dijottam Krishnamurthy, Brandon McMahon, Krishna Pelutla, and Thomas Steinke. And ignore confidential Google DeepMind because I could not remove from the template. Good. So this talk is about large-scale private learning on data streams and the BLTs. Trust me, it's not the sandwich, but okay. So what we're going to cover today, we're going to cover some initial background on two classes of algorithms which are pretty much used very commonly for training large-scale machine learning models with privacy. One is called DPHD and DPFTRL. And this would relate to Sophia's talk on continuous release models. And then we'll look at very specific type of factorization models like Toeplitz factorization. And there I will describe what I mean by BLTs, which is not the sandwich again. And in the third part of the talk, we'll give some empirical optimization for this BLT objects. And finally, I'll end with some concluding remarks. Okay. So the first part is private federated learning. And this algorithm called DP, follow the regularized leader. For people who are conversant in online learning, FTRL is a very standard algorithm for online optimization, and I'm putting DP on top of it. What do I mean by that? Okay. So there is this algorithm called DPHD, differentially private stochastic gradient descent. This has been studied by 3 papers at least, and is one of the most widely used algorithms for training models with differential privacy. So the idea is that you have a set of data, and what do? You sample a mini batch of size k uniformly at random, compute the gradients on each of the data points in that mini batch, clip the gradients, average it, and add some Gaussian noise to it. And once this average gradient has been added noise to, you just do standard HGD update. That's it. There are parameters what are called clipping norms and noise multipliers. If I had more time, I would have explained what these are and what do they mean. For this talk, you don't need to care about them. Think that clipping norm is 1, and noise multiplier is essentially the standard deviation of the noise which I'm adding to. Okay, good. And whatever I'll be telling will be on Gaussian noises. So one of the challenges for implementing this algorithm, in particular in the settings of federated learning, where you have like a distributed data set and you are getting devices at whenever the devices wakes up and gives you data, you cannot sample from the sample a uniform mini batch. And this slide essentially tells you why it is hard. You'll have diurnal patterns. You don't even know how many active devices you are. While taking gradients, you have to first make sure that devices are active. It is connected to the power, and it is connected to Wi-Fi. You don't want to drain your battery for training Google's models. So it is hard. In an earlier work, we did give some feasible protocols, but it required extreme changes to the infrastructure that was required. And the amplification guarantees what I mean by amplification is like the fact that I'm sampling a small set of data points from a large training data set. This gives you inherent privacy protection, and this kind of privacy amplification required access to like large number of available data devices at any training step, and that essentially slowed down learning. So we came up with this algorithm called DP, follow the regularized leader. The initial version was from a paper of mine with Adam Smith, and then in 2021 we gave a more refined version in Kairos et al. And the idea is that here you don't have amplification at all. What you sample the next batch of devices, whatever you get, do pretty much the same thing, compute per example gradients, clip the gradients, and then you feed into this right now black box object DP matrix factorization, and that magically gives you a differentially private version of the prefix sum of the gradients what you have seen. And this would start being similar to what Sophia has spoken about. And then you do your standard gradient descent update and move on with your life. This is DPFTRL. The major advantage is that you have no amplification. You just get a data in stream, process it, go forward. Good. Whatever I'm talking is not a theoretical artifact. It is actually running in production. So if you have a Gboard, Android keyboard, and if you are using next word prediction for your Android keyboard, this algorithm is actually running in production. It is running for all the languages listed here. And there is a blog post initially, Brandon McMahon and I wrote for the initial version, which was for European Spanish. Now it is for all these languages, and there is a full-blown paper on federated learning on Gboard models with differential privacy. Good. So beyond the marketing slide, let's go to technical details. So let's try to deconstruct the HGD update, stochastic gradient descent update. If you, and this I'm telling without projected, there is something called projected gradient descent. What I'm talking here is no projection, and typically in deep learning mode training, you never do projection. But if you deconstruct the HGD update, the recursive update, then you will see essentially that you have an initial state, and then you are essentially computing a prefix sum of the gradients what you have seen so far with some scaling learning rate, right? And now the thing that is interesting now is the prefix sum of the gradients of what I have seen, and I want to protect the privacy of that. Good. Yeah. Good. Huh? Learning rate is held constant for this time being, for this conversation. We can make modifications, but easier to present. Good. So FTRL, the follower the regularized leader, this had multiple names, follow the regularized leader, dual averaging, and I'm forgetting the third one. Independently invented by 3 sets of papers, McMahon in 2010, Ducci et al. In 2010, and Lin Jiao in 2010. The FTRL updates essentially says that instead of doing an HGD update with the gradients, I can take the prefix sum of the gradients, have a linear function on top of it, and I have a L2 regularizer, and I minimize that. And without operating on constraint sets, these 2 updates are equivalent if the initial state is assumed to be 0. So what I want you to remember from this slide is that you really care about the prefix sum of the gradients what you have seen so far. And since I'm talking about gradients, these are adaptive streams. Like you compute the next gradient based on the previous ones. Okay. The results, whatever I'm going to tell today, will work on adaptive streams. But why they work on adaptive streams, I will push it under the rug. Yeah, good. So FTRL, you have gradients. You want to compute the prefix sum of the gradients. Observation is that yeah, this I already told that to privatize the FTRL, only need to compute the prefix sum of all the prefix sums with DP. Just start with a warm-up approach. If I add independent noise to each of the gradients, this is what we call DP-HGD, like without amplification. Then you will see that you will add noise in the order of square root of n. If n is the number of steps, you will add noise in the order of square root of n. This is just like standard variance bound. If you use amplification, you go to order 1 over epsilon for the last prefix sum what you computed. So this is just to keep the scale in mind. I want to be closer to this number than this number. So what I will do is that I will change the perspective a little bit. I will write this prefix sum, just pretend this gradients are dimension 1. If they're not, these things work, but pretend the gradients are dimension 1. I will write this prefix sum estimation as a matrix vector product. You have a lower triangular matrix of all ones, and you're multiplying with a sequence of gradients, okay? And you want to compute this while preserving differential privacy. Good. So formally the problem is you want to factorize a matrix, this lower triangular matrix of ones, into B times C such that C times the gradient vector plus noise satisfies differential privacy. Forget about what ZCTP is. This is one form of differential privacy. Satisfy differential privacy even when the sequence of G's are chosen adaptively, because I want to run it for gradients. And second is a little bit of math. What I do is that I write the error B times C times G plus the noise minus the actual data, and I'm measuring the error in the L infinity norm. Essentially tells that B times noise, the L infinity noise of the B times noise is minimized. So I have this by objective. One, I want to preserve C times G to be differentially private, and I want this thing to be minimized. From here on, you can forget about differential privacy. What I really want to minimize is the factorization norm to get the best error. What I really want is that the max column norm of C times the max row norm of B, these 2 products are minimized. If it is, then I can run with my noisy gradient descent, and these things work. So that's the part which I'm making the jump. You really need to care about the factorization norm of B and C. I want to factorize the lower triangular matrix of ones into B and C such that the max L2 norm of B and the max column L2 norm of C, this product is minimized. Okay. So this is also called the factorization norm, and this particular norm has been studied extensively in computational geometry. So what do we know so far? So we want to minimize this, and from now on I will represent this as max error with this matrices B and C. So what we know so far, this is from a paper from Matthias and Nikolov Talvar, I'm forgetting the first person's name, pardon me for that. So the max error is 1 plus 1 over pi times log n. So I wrote these exact numbers down. These numbers are not that important, these two are important. Like I really want to hit the constants. Okay.
This is for just that
lower triangular Toeplitz matrix of ones. Okay. Yes, and we know this is tight, like it's plus minus 1, log n over pi plus minus 1. So there is a lower bound also, tells you that. Okay. So the constraint is, so one of the constraint of, this error is good. We can factorize these matrices. Let's say we can write an SDP to factorize these matrices, minimizing the error even empirically. But the issue is that once I try to implement the algorithm, it requires me to pre-compute the noise. The reason is when I'm running the algorithm, the B, when I'm multiplying, I have to instantiate the algorithm, right? So I wrote it as a factorization of a norm, but ultimately I have to instantiate the algorithm in a gradient descent process. So to compute the noise at each step when I'm adding to the gradient. And once I try to do that, I need to know what the previous noises are, right? So to pre-generate the noise, and this B can arbitrarily correlate all the noises what I've seen so far. So I need to pre-generate the noise, and this is prohibitively expensive if we are running larger models, because up to this point I told the gradients are one-dimensional objects. Really they are not. They're like trillion parameter models today, and saving that much of memory is like extremely challenging. So I don't want to do that. Compared to DPHGD, where I just generate a noise on the fly, add to the gradient and move fast, that has very less memory over it. It's like the space memory is like exactly as the gradient space. So I want to be closer to DPHGD, but still have the error close to this quantity. Okay. So that's the setup we are operating on. How much time I have? This is the first part, so good. Okay. So this is exactly what I'm saying. So dimensionality of the noise is typically number of steps I'm running for times the number of model parameters. Prohibitively expensive for large scale learning. And in comparison, DPHGD noise can be generated on the fly. So much memory blow, not so much memory blow up. So question, can you design algorithms with error which is comparable to this 1 plus log n over pi, and with memory comparable to DPHGD? What I really mean is like the algorithm where I just add fresh noise at each step. Okay. So let me pause for a second here and say that like for the next part of the talk, what are we going to say? There is some part of like technical math we need to do. But the biggest challenge we faced in our work is to find out what tools to use. It was absolutely unclear to us what tools, and we had like a bunch of false starts. And this is just not for motivating people, this is actually true. So even if some of the things look trivial in the hindsight, searching for the right tools was pretty hard. So, okay. So now we come to Toeplitz factorization and the BLTs. And before this talk, I did not know what B and LT stood for in the sandwich. I thought it was beef, lamb, and turkey. Now I know it's bacon, lettuce, tomato. Okay. I don't eat bacon, so yeah. So now let's go to Toeplitz factorization and the BLTs, which is a new operator we introduced. Maybe this has been studied in the literature. Please correct me. So we did not know of it, so we just gave it a name. We called Buffered Linear Toeplitz operators. So where does Toeplitz factorization come in? No. So let's give it some names. A is the query matrix because that's what is hitting the gradient. B is the noise correlation matrix because that is correlating the noise across the time steps. And C is the scaling matrix because it is scaling the data vector, right? Good. So easier. Recall, I want to minimize the max error. Now, the class of matrices I will look at, B and C, will look at Toeplitz square roots, meaning that B is a Toeplitz matrix. A is a Toeplitz matrix is obvious. What is a Toeplitz matrix? Just to kind of, oh, sorry, I should have told this. So A is a lower triangular matrix. A matrix is Toeplitz if its diagonals are of the same quantity. In particular, the Toeplitz matrix can be defined by a single column. Right? That's the, yeah. So now I'm looking at Toeplitz square roots. So what I will do, I'll make B and C to be equal. and I will factorize in that way. So basically, I take the A matrix and take the Toeplitz square root of it. Good. So what is our first theorem? A version of the upper bound existed in an earlier paper by few folks, and ours both gives a strong upper bound and actually proves a lower bound. So what we show is that if I just restrict myself to the Toeplitz square root, then my max error is the initial 1 plus log n over pi plus this constant, 0.5772. Okay. So why am I showing this? What this emphasizes that going to Toeplitz systems is not making you lose too much. It's just an additive constant. Okay, and it requires some work to show that taking Toeplitz square root is optimal under any lower triangular Toeplitz factorization. If I give you this matrix instead of, and I tell you that the restriction is that B and C has to be Toeplitz matrices and they have to be lower triangular, the fact that B equal to C is the right choice requires a proof. In fact, in the initial submission, we had a wrong proof, which we corrected and sent. Now going to Toeplitz factorization with BLTs. This is just to remind what the problem was. Okay. So what I really want is that I want to efficiently generate in low space B times the noise vector, right? Because that's what gets added to. Like B is the correlation matrix, B correlates the noise, and Z1 to Zn, you can think like these are Gaussian noises. Okay. So this is what comes the actual definition of the BLTs, the buffered linear Toeplitz matrices. So these are the matrices where, remember, you are talking about Toeplitz matrices. Defining one column is sufficient for me. So these matrices are defined. The entries are defined as BK is U is a vector, which is the projection vector. W times K, W is a matrix, D by D matrix, and V is the initial state. So U is the projection vector. W is what is called the companion matrix. It will be this is a very standard term. It will be obvious why it's called companion matrix. And V is the initial state on which you are operating on. Okay. For dimensionality, U and V and RD is RD vectors, and W is a RD times D matrix. There is one D missing here. Okay. So I will restrict myself to this set now.
Sorry, just to understand.
Yeah.
So you vary K from, I guess, 1 to n to get n numbers.
Yes.
And use that to define a Toeplitz matrix.
Yes.
Where it's all these powers of these.
Yes, exactly. Good. So once I define this, something interesting happens. This thing can be written as a constant recurrence sequence. And this is a well-studied object. Now I'm seeing like these are the tools we'll start slowly using. So constant recurrence sequence. So B times zk is the kth entry of B times z is U transpose times sk plus 1 is a state. So I'll maintain a state, and every time I need to compute the inner product of B times z, the kth entry, I will just project it onto U and output it. And how do I maintain the state? Sk plus 1 is the V is the initial state times zk plus W times sk. So it's a recurrent state update. You only need to remember the state. And the state is D cross 1. Good. Okay. Now once I write in this particular form of BLTs, I still need to get that error, 0.577 over pi, right? It turns out that this has very close connections to what are called rational functions. Oh, before going there, sorry. So what we show, so once I told you this, now I've defined what BLT is. What we really show is that there exists a BLT factorization. So I'm defining the B matrix as a BLT operation, which will have error 1 plus log n over pi plus 0.572. This I had for Toeplitz factorization, plus a term mu, and the time and space is log squared n over mu. I don't think log squared is tight. It is we should be able to get down the power down, but via rational, the next tool that I'm going to show, the results what you're using, through that technique, I don't know we can improve on this squared term. Good. Oh, by the way, and this is theory. In empirics, we show that we don't even need that many buffers. Constant number of buffers are sufficient. So maybe something magical is happening. So let's give the proof sketch for this, and that's what we introduce. So first, we'll use a rational function representation of BLTs. This is very well studied in math literature. So what is a rational function? We are defining in a very particular way. It is a ratio of two polynomials where the numerator polynomial has degree d minus 1, and the denominator polynomial is 1 plus up until which goes to degree d. So the denominator has degree 1 more. Then there are other formulations of it. This was just most convenient for us. And then I can write the Taylor expansion bk x to the power of k, okay, where bk is given by so the coefficients would be the coming out of the coefficients of the rational polynomial. So, and it is well known that BLTs can be this particular, if once I did bk's to be this form, they can be represented as rational functions. Okay. So now going to our original problem of prefix sum, if I write the query matrix as a rational function, what I mean by that, I want the first column to be generated by the coefficients of the Taylor expansion of a rational function, then that is 1 over 1 minus x.
Generating function, right?
The generating function, exactly. So I'm taking the generating function. So now I say that I will set b and c to be equal. So only thing that makes sense to make is 1 over square root of x, 1 over c as 1 over square root of 1 minus x, right? Now I have to try to make an approximate. This is not a rational function. So I need to approximate this with a rational function. And whatever approximation I get, I will fudge the error into c. So my c would not exactly be like 1 over square root of 1 minus x, it will be something else. But b times c would still be a. Good. So what do we do? First, we represent the noise correlation matrix with the generating function b as 1 over square root of 1 minus x. Then we take a heavy hammer. The heavy hammer is that we want to approximate square root of 1 minus x for all x on the unit disk. I will say one sentence about why we need over the unit disk with degree d rational function to error exponential 1 square root of e to the power minus root d. So in rational function theory, getting this kind of error e to the power minus root d was known for a very long time. From 1964, actually, this is called the Newman approximation, which gives you e to the power minus square root of d. But unfortunately, the approximation is only over the real line. And remember, I don't need to approximate this function. I want an approximation which approximates the coefficients of the Taylor expansion of the function. So I need to do something else. So that's the reason why you need this approximation over the unit disk. And to do the unit disk, once we get an approximation, we would be able to use Parseval's identity to shift from the function, the error in the function evaluation to the error in the coefficient evaluation. Two challenges. First, so getting this rational function approximation over the unit disk, we use this paper from Gopal and Raffandel from 2019. They had a proof sketch. They really did not have a proof. We wrote the proof in the paper, not claiming credit for that, but yeah, it's a nice proof. And then we also needed to ensure that this Parseval's identity goes through. We can't use direct Parseval's because this function, the Taylor expansion of this function is it does not converge. So what we needed is a weighted version of the weighted version of Parseval, meaning that we will not operate on the unit disk, unit circle, integrate over the unit circle. We'll actually integrate over a smaller, slightly smaller radius of the unit circle. So we needed weighted Parseval. And then once we get this pieces out, we'll translate it to the max error objective. So this is how the proof goes through. Okay. Good. Obviously, I did not give details of the proof. This is at least the pieces of the paper. So, okay, going back to the question, yes, we can match up until the PhD with polylogarithmic overhead in the space, blow up in memory. Okay. Going to empirically optimizing for the BLTs. Now, I'll throw away theory. I'll just empirically optimize for this quantity. Okay. So, represent the Toeplitz matrix as sum of partial fractions. Okay. one point is that I will assume that for the optimization, the empirical optimization, I'll assume that the poles are unique. Once I do that, you can have another representation of the coefficients of this the Toeplitz system as linear combination of van der Waals basis. So that once I write in linear combination of van der Waals basis, which is basically alpha I times theta I to the power of k, summation over alpha i's, I get a complete closed form expression for the max error in terms of the roots and the poles. So now I hammer it with LBFGS to optimize for that one with respect to this mu and omega and theta I. It turns out that this optimization empirically is not that easy because I mean there are reasons for it. Once I'm approximating, when I'm putting the poles, I'm getting very, very close to 1. And once I go to close to 1, remember I'm trying to approximate 1 over square root of 1 minus x. So x getting close to 1, things will start blowing up. So you need to have like enough number of tricks to make the algorithm stable. Stabilizes. And what you get is bunch of plots. Forget about the things which are not in the red boxes. I was lazy in like creating a new plot. RA BLT is the rational approximation BLT what we have. That is the blue line, and the green one is optimization BLT with d equal to 4, like the degree is 4. So really up until like 10 to the power of, this is till 10 to the power of 6, up until 10 to the power of 10, we needed like degree like to be 6 to 7, not more than that. Like this one is for 4. One thing also I wanted to show you is that the binary tree mechanism is nowhere on the chart. Like this shoots up. There are shoots up for binary tree mechanism, any form of binary tree, and there is a reason for it. Like if you look at the binary tree, and the leading constant, it does not even recover the leading constant. So we needed this, and yeah, empirically we show that like if we optimize for these BLTs, you actually get like much tighter than what theory has. Like theory we are saying like log squared n buffers, and in empirically like 4 to 6 buffers are good for like in 10 to the power of 10. Good. So going to conclusion, what did I tell you? I told you about two algorithms, DPAGD and DPFTRL. These are the algorithms which are used in practice, and there are production deployments for both of them. We needed memory efficient solution. Then I told you about the Toeplitz factorization and the BLTs, and BLTs were a memory efficient way of approximating Toeplitz systems. And then I showed some empirical evaluation. We showed that if I explicitly optimize for the BLTs, then I get much tighter quantities than what theory suggests. It turns out that there is actually a reason for it. So the reason that the empirical optimization actually works, when I was solving for the Toeplitz system, I was solving for the infinite Toeplitz system. So the mechanism I was giving you for the analytically was a single mechanism which would work for any n. But when I'm optimizing for, I'm only optimizing for this fixed set of n's, which means that if I write the Taylor expansion, I just need to match that only first 10 Taylor coefficients rather than matching the whole sequence. We don't know how to take advantage of that analytically. So that's one. Yeah. So first is improve the dependence on the logarithmic dependence on the error on the number of steps. Design better analytical BLTs by explicitly analyzing the Toeplitz system in the finite world. What I mean is like I really need to match the first 10 coefficients, nothing else. Then the other thing that is important is that this is a recursive process, and when I'm instantiating this, there will be error accumulation. So we have seen that these things are stable, at least from the experience what we've done, but we really need to understand the numerical stability of these algorithms because we are getting very, very close. The poles are getting very, very close to 1, and this numerical stability is important not for utility purposes, but actually for ensuring privacy. So formally understanding like what is the numerical stability of this quantity is important. This is not an open question, but more of a future direction or current direction. We are currently evaluating BLTs for production systems. So it's not just and this is the paper. Yes, please.
So in one of the slides you mentioned that you assume that the poles are unique. So how do you remove that assumption?
Oh, so I did not not in the theorem. So I assume the poles are unique is when I'm optimizing for it. I will make sure that the space over which I'm optimizing for, they have unique quantities.
Yes, thank you once again.
we have just enough time for a quick break.